Welcome to Ask and Learn.
The situation here is that the crystal is in the shape of a cube, and we're interested in finding the rate of change of the volume with respect to x when x is 3. So the volume of a cube is x cubed, and the derivative of that, dv dx, would be 3x squared. So then dv dx for x equals 3, we're going to substitute a 3 in there for x, and we get 3 times 3 squared, and that would be 27. And the units on volume would be millimeters cubed, and the units on x would be millimeters. So what this is telling us is that at this particular size of cube, the volume is growing at a rate of 27 cubic millimeters for every millimeter change in x. And in part B of this problem, we're looking at surface area. So to get the surface area of a cube, you're going to add the area of every surface. And for this cube, every surface has an area of x squared, and there are 6 of those. So the surface area is 6x squared. Notice that the derivative of the volume is half of the surface area. Now let's take a look at that from a geometric perspective. So suppose that the cube grows bigger, and the side length is now delta x. Or the side length is now x plus delta x. So we added delta x to each side. So the new volume would be x plus delta x quantity cubed. And the old volume was just x cubed. So the change in volume is a new volume minus the old volume. And let's work that out algebraically. So the change in volume is going to be, we have to cube this binomial, and so you're going to have to work that out either using the binomial theorem or just multiply x plus delta x times x plus delta x times x plus delta x. Do that very carefully, and you're going to get x cubed plus 3x squared delta x plus 3x times delta x squared plus delta x cubed. And then we still have the minus x cubed at the end, subtracting the volume of the old one. Notice that we can cancel the x cubed and the minus x cubed. So this is our change in volume. And suppose we want to know the change in volume over the change in x. So let's go ahead and divide this by change in x, delta x. And while we're doing that, let's factor out a delta x from the numerator. So we have delta x times 3x squared plus 3x delta x plus delta x squared. That's over delta x, so we can cancel the delta x from the top and the bottom. And all we have left is that the change in volume with respect to a change in side length is 3x squared plus 3x times delta x plus delta x squared. So if delta x is small, then the second term is going to be very close to 0, and the third term is going to be very close to 0. And the rate of change of volume with respect to x is going to be approximately 3x squared.